We begin today by looking at alkenes and alkynes. And so what we're talking about here, we're still talking about hydrocarbons. But now we're talking about hydrocarbons where we aren't exclusively featuring single bonds. And so we're looking at alkenes, which feature one or more double bonds, and alkynes, which feature one or more triple bonds. And so if we had the situation where we had both, then we would call it still an alkyne. We just go based upon whatever the most prominent feature was. So common example of an alkyne is acetylene. Acetylene, its formal name is ethene, or excuse me, ethyne. But most commonly we refer to it as acetylene. It is a 2-carbon alkyne. Now, what makes these different is the fact that because we've got that double bond or that triple bond in there, what we're going to start referring is this idea of unsaturation. These hydrocarbons are unsaturated. Remember, saturation was based upon hydrogen. If every carbon had as many hydrogens on it as possible, we referred to that compound as a saturated hydrocarbon. Alkenes and alkynes, because they've got double bonds or triple bonds there, we don't have that saturation anymore. We don't have that full complement of hydrogens. And so we call that group unsaturated as a result. Now, because of that lack of saturation, there is going to be introduced an additional kind of chemical reaction for these alkenes and these alkynes, because now we have the capability of saturating them. And we can saturate them with a lot of different things, most commonly with hydrogen, which would turn the extra bonds into just regular single bonds with hydrogen groups. There are other kinds of reactions that can be done in the same kind of way. And we'll get to those in a minute. As far as identification is concerned, we can identify alkenes based upon the presence of this double bond. Now, as far as the naming system is concerned, we're going to get into naming a little bit. Basically, all of the naming constructs that we looked at last week apply here as well. All of those prefixes apply. The identification of the longest chain, it applies. The only thing that is kind of different is that because in certain kinds of alkenes, that double bond could be in multiple locations, we have to identify it by position. We have to use a number to identify where it is. Now, in ethene, it's a moot point. There's only 2 carbons, so the double bond really only has one place where it can be between the 2 carbons. It can't be anywhere else. And with propene, I've got 3 carbons. It's the same kind of deal. Even though there's a possibility that if I'm looking at my 3 carbons, there's a possibility it could be here or there on one side or the other. If we're going from a naming standpoint, remember we always number in whatever order gives us the smallest combination. We would describe both of these as one propene, because the numbering system is always going to be lower starting at 1 than starting at 2. But beyond that, obviously it gets a little bit more complicated. And that's where we would have to use some of that numbering that we were talking about last week. For alkynes, everything we just talked about with double bonds, we just replace the word triple bond instead. We identify alkynes by the presence of triple bonds. In the case of ethyne here, we see that we're going to have a couple of bonds, or excuse me, a single triple bond between the two carbon atoms. So as our first kind of progress check here, all we want to do is identify these compounds as either alkene or alkyne. And again, it really just comes down to what do we have there? So here I can identify I've got a double bond. Double bond should tell me I'm dealing with an alkene here. Here I have a triple bond. I know I'm dealing with an alkyne. And again, if I had both in the same molecule, it would still be an alkyne. The presence of that triple bond kind of supersedes the presence of the double bond in terms of the naming. Is that? All single bonds. So yeah, no extra bonds, no doubles, no triples. And so those are the three sets of hydrocarbons that we can talk about. Alkanes, everything's a single bond. Alkenes, we've got at least one carbon-to-carbon double bond. Alkynes, we have at least one carbon-to-carbon triple bond. As I mentioned before, the naming systems here are pretty much the same for alkenes and alkynes as they were for alkanes. We're using the same prefixes. We're using the same kind of structure. So, again, we kind of think about it, find the largest carbon chain, name the chain, start adding on those side groups like train cars in front of it. The only difference is in the ending. For alkenes, instead of ane, they're ene. And that's what gives us that ene sound at the end of that molecule's name. For alkynes, we would end that with yne, ine, instead of ane or ene. And that's what signifies those. Again, if we have ring structures, then we just put the prefix cyclo in front of whatever it is that we're looking at. What? 41. All right. So now we need to go back and start looking at these from a perspective of naming. And so once again, it comes down to a matter of following the processes that we were learning last week. So going back to Thursday here. First thing we need to do is we need to identify the longest chain. Now, it so happens that if I number this chain as so, or this chain going down, I end up with the same number of carbons either way. So if you watch that Melissa Maribel video that I sent you on Friday, this is kind of one of the things that she was highlighting, was making sure that we find the longest chain. Now, in this particular case, it doesn't matter. Both are the same. So what really comes down to is, let's just keep it simple and just keep everything up. I have two possible ways of numbering here. In purple, I could name this methyl group at 2 and this alkene bond at 3. In blue, I could name the alkene group here at 2 and the methyl group here at 4. Now, if we go off of what we talked about on Thursday, we would go with the purple numbers. What we talked about on Thursday was that we always go with the lower combination. When we get into alkenes and alkynes, what we start to establish is that there is kind of a hierarchy of needs. And so when it comes to numbering the alkenes and the alkynes, that's the number that always takes precedent. That's the one that we need to think of first. So even though the purple numbers give us a lower combination, the fact that the alkene is being numbered at a lower number here means we're going to go with the blues. And so one of the things that's very tricky, I wanted to make sure I said it right. That's why I opened it up to your book to double check. One of the things that's tricky about organic nomenclature is that there are kind of these tiers. There are kind of these levels to the naming rules. Now, luckily for us, we don't have to examine all of the different nuances of all of the different rules, but we do need to know this one. So from that standpoint, we want to make sure that we've got the 2-ene as that particular group and the 4-methyl as this one. This is a 5-member chain. So 5 we know is pent. So now we've got to put it together. We put it together. Without the side group here, this would be 2-pentene. Without the side group, it would be 2-pentene, because we would be saying that that double bond starts at the second carbon and goes to the third. That's what the 2 indicates. But because we have this sidecar on here, we need to add that as well. So 4-methyl 2-pentene is the full and correct name of this compound. It would not. The only reason you would be putting commas in the names is if you had the same side group. So if the 4 and the 2 were both methyl groups, then you would put 2, 4 dimethyl, whatever it was. But if the two groups are different from each other, and they are here, one of them is a double bond, the other one's just a methyl side chain. If they are different from each other, we don't use commas, we would use dashes. All right, this one's a little bit simpler. We don't have any side groups. What we do have, we have 1, 2, 3, 4, 5, 6 carbons. So we know this is going to be hex. It's just a matter of numbering. Do we number right to left, or do we number left to right? So what we're looking at is the difference between 4 and 2. Obviously, 2 is going to be the smaller number. So 2 hex ine would be the name of this compound. We have no other side groups, so I don't need to put any extra cars on the front of it. All that we need to do is identify where is the triple bond and how many total carbons are in the chain. So 6 carbons meant that it was hex. The triple bond means that it's ine, so there's your hexine. The 2 is just the location. It's on the second carbon. So again, that obviously means that the triple bond is going from the second carbon to the third. Alexis? It's all about the lowering of the number. We always want the smallest combination of numbers as we can, provided if there are multiple groups that the double bond gets the smaller number. So the reason this one we went with the top instead of the bottom is because that double bond got the lower number. Right. Yes, because if we went just off of numbers, the purple numbers would have made more sense. 2 and 3 is smaller than 2 and 4. But the double bond ranks higher than the substituents do. And so it gets the preferential numbering. Olivia?
This is only for the alkenes and alkynes, not alkenes.
For alkanes, we would just number based upon whatever gives us the smaller combination, because all of those substituents are considered equal. But for alkenes and alkynes, that double bond, that triple bond is of a higher importance. And so it gets the lower number by default. All right, other questions here? All right. What if we have something cyclical? Well, in a ring, we can number in any direction starting from any carbon. So what that means is that when it comes to numbering, we're always going to number that double bond or that triple bond starting at 1. And then numbering in whichever direction goes through that double bond. So in this case, I've got a double bond and a methyl group here. The double bond gets numbered either as 1, 2, 3 going counterclockwise, or if we went clockwise, starting at 1 at the top of the pentagon and going around. Either way, the position of that double bond would be at 1. The reason we call it 3-methylcyclopentene instead of 5-methylcyclopentene is because of the direction that we went. Again, we go the direction that gives us the lowest combination of numbers. Why is there no 1 for the cyclopentene? Because since there's only 1 double bond, and because of how we number, it's assumed that it's going to be in position 1. And as we've stated a couple of other times, if something is assumed, we generally don't write it. Okay, so if we look at these two then, in this first one, since there are no subgroups, this would just be cyclohexene. Hexene, because we've got 6 carbons, 1, 2, 3, 4, 5, 6. Direction doesn't matter here. Because there are no other side groups to number. So I could have started there in this position. I could have started in this position and gone counterclockwise. It wouldn't have mattered. Well, it wouldn't matter because you're always going to put the number 1 and 2 on the double bond. So when we have ring structures, that 1 and 2 are going to bracket that double bond. Similarly in this one. Now there's 2 different ways of numbering. We can number clockwise as such, or counter, again, starting at and bracketing that double bond. And we can see here clearly the numbers in purple are going to give us the lowest combination. I've got 2 methyl groups here. This is a methyl. This is a methyl. 2 methyl groups would give me dimethyl, both at position 3. So this would be 3, 3 dimethyl cyclopentene. So again, the thing to do is kind of start with your base. What is it? And then just add to the front as is necessary. So what is the base of this? Well, the base of this is a cyclopentene. I've got a 5-membered ring with a double bond in it. So that's where the cyclo comes from because it's a ring. The pent comes from the 5. The ene comes from the double bond. There's my cyclopentene. Now, what else is attached to it? I've got 2 methyl groups attached to it. So that's dimethyl. Where are those 2 methyl groups? Well, they're both on 3. So that's where the 3,3 comes from. So I got to put them all together. All right, questions with these? Because it's dimethyl. There are 2 methyl groups, you have to give the location of both. So you can't assume that they're both in the same location. That's why we're being redundant there for specificity. We want to be very sure that you understand that both of those methyl groups are on that third carbon. Because otherwise it would make sense if we had a series of assumptions, but without those assumptions, you'd be going, okay, it's dimethyl, but I only see one location. Did they forget? Or is it on the same carbon? Really wouldn't know unless it was established that that's how we did it. And so from a clarity standpoint, it was decided long ago, every subgroup, every side group gets a number.
It's also if we were to give it that.
We would have a hard time determining with certainty where that second methyl group would be. Because it's one carbon.
Drawing one of these from, well, obviously, okay. When you're drawing the structure from the name, how do you know where to put double bond?
Okay, so if it's cyclical, it's easy. You just put it wherever you want. And that's the one of your ring. And then you just number from there. For the other ones, let's say it's not cyclical. Well, you've got the benefit, you have the name in front of you. So you just build it however you best see fit. So number it from left to right, because that makes the most sense. And then you just build backwards. Start with cyclopentene. Okay, I've got a 5-membered ring. It's got a double bond in it. Okay, it's dimethyl. I need 2 methyl groups. They're both on position 3. Here's position 1, 2, 3, my methyl group, my methyl group. Start in the middle and work your way out. And honestly, you'll have a lot more difficulty in terms of just making sure that you've got all the groups on there than if you're just trying to do it, any other way. All right, let's get into something else here. Isomerism. Now, we already talked about structural isomerism, the idea that the same chemical formula can give us multiple compounds. And we can just start moving around methyl groups to kind of compensate. This is a different kind of isomerism. This is the kind of isomerism that happens particularly with double bonds. So, easy way to simulate that is like it's showing in the picture here with your fingers. If your fingers are representing a double bond, understand that on either side of that double bond, we've got other stuff. Cis-trans isomerism says there is a difference between when those groups are on the same side of the double bond versus opposite sides of the double bond. They're going to have different properties because of where those bonds are and how those other groups are going to be able to interact and relate. Cis, Latin origin, means same. We've got the groups on the same side of the double bond. So if we think about it as up or down, they're both on the upside or they're both on the downside. Trans means opposite. They are on opposite sides of the double bond. So we've got one on the upside, we've got one on the downside. So this is a different kind of isomerism. This is called a geometric isomer, where, again, same chemical formula, same structure, because we got a double bond in both cases. But its geometry is different because of the position of those groups in relation to each other. And the reason this happens is because unlike single bonds, where we had that bond that was able to rotate and move around, that double bond kind of locks the position of that molecule. Double bonds and triple bonds can't rotate. Now, the reason we don't have cis-trans isomerism with triple bonds is because of their geometry. Their geometries are linear. And so there's only one configuration, and it's opposite. Because the bond itself is a linear bond around that triple bond. But with double bonds, the bonds are 120 degrees oriented to each other. It's kind of like a triangle. And so you can have 120 degrees going in one direction or going in opposite directions. And because that bond doesn't rotate, those two structures would be definitively different from each other. And they'd have slightly different properties. As far as naming is concerned, it's just another prefix. We use the prefix cis or trans in front of the numbering of those groupings. So when they're both on the same side, like the bromo groups are in this first one on the left, that would be the cis configuration. We would call this cis 1,2-dibromoethene. When they're on opposite sides, that'd be trans 1,2-dibromoethene. They're both 1,2-dibromoethene, but because of that geometry configuration, they are different from each other. And they would have differences that would be notable, particularly in reactivity. Okay, we've got 3 compounds here. We want to name each of them using cis or trans prefixes as necessary. So first one. What we should recognize in all of these are all 4-carbon chains. 1, 2, 3, 4. 1, 2, 3, 4. All of these are 4-carbon. So these are all butenes. Because again, prefix for 4, bute, ene, because these are all alkenes. Now in letter A, we have chloro groups here, and we have 2 of them, so this would be dichloro. The name without the cis and trans would just be 2,3-dichlorobutene. But since orientation does make a difference here because of that double bond and way those chlorines are oriented, we need to add that extra prefix. And since the chlorines are both on the same side of this double bond, they're both on the upside, this would be cis 2,3-dichlorobutene. Here I have a pair of bromo groups. So this would be dibromo. We can see that they are on opposite sides of that double bond. One is in the up position, one is in the down position. So this would be trans. trans 2,3 dibromo butene. In this last one, we have hydrogens as the subgroups. Those aren't subgroups. Hydrogen is just what's supposed to be there. So our name's gonna be a little bit simpler here. We still have cis and trans because we can see that the chain is definitely coming through on the upside and the downside. So this is trans. This would just be trans to butene. So even when we don't have subgroups, that double bond does carry a little bit of significance there, because we could see a situation where, let's say that this methyl group on the chain flipped around and we had this kind of configuration instead, we would recognize that's structurally different from a geometry standpoint. And so that would be cis butene or cis 2 butene instead. Right, any questions with cis and trans? Mm-hmm. Yeah, so yes, I want to say this is Latin, but the Latin root cis literally means same. So we're talking about the same side of the double bond versus opposite sides. Well, it depends on how it's drawn. So in these kinds of configurations, we see them as up down. Turn it 90 degrees, it'd be left right. So it really is just kind of evaluating, okay, I've got my double bond here. Which direction is it coming from? And is it going out the same direction, or is it going out the opposite direction? That's your cis versus your trans. And so it doesn't matter if the double bond is vertical or horizontal, you're looking at it the same way. In and out the same way, cis, in and out opposite ways, trans. Okay, last thing out of this chapter are the addition reactions. Addition reactions are basically how we turn these unsaturated hydrocarbons into saturated hydrocarbons. And the reason why these products are shown is because most of these contain partially hydrogenated oils. That term, partially hydrogenated, is basically what we're talking about here. We're talking about the hydrogenation, the addition reaction, where we take hydrocarbons that are unsaturated, expose them to hydrogen to make them saturated, or make them more saturated in the case of a partially hydrogenated one. So there are two primary types of addition reactions that we are going to be interested in. They are hydrogenation reactions and hydration reactions. They are exactly what they sound like. A hydrogenation reaction is the addition of hydrogen. Hydration reactions are the addition of water. Now, in terms of what is necessary to create these products, usually we need some kind of a catalyst involved to help make the reaction a little bit more easy to do. And you can see some examples of what those catalysts are. For hydrogenation, we're usually talking about some kind of inert metal, platinum, palladium, nickel. For hydration reactions, we're always talking about strong acids. But the main point is that at the end of this process, basically, we go from having some kind of a double bond or a triple bond. And if we add hydrogen to that double bond, it's going to turn it into a single bond. Those extra hydrogens are going to attach across that double bond in turning it into a single bond. So hydrogenation reactions look like this. I've got my double bond, and I can see that double bond, if I add hydrogen across to it, that double bond is going to break, and the bonds are going to form across the carbons in that bond. Now, if I have an alkyne, that process is going to happen twice. And so we go from unsaturated, having a double bond or having a triple bond, to now saturated, where all of the double bond and triple bond character is gone. All of the hydrogens that were there as alkanes are restored. So let's do this last study check, and then we'll call it a day from here. Write an equation for the hydrogenation of 1-butene using a platinum catalyst. 1-butene, so we're talking about 1, 2, 3, 4, and double bond, CH2, CH, CH2, CH3, plus hydrogen. For catalysts, we always put catalysts above the arrow. The reason we do that is we're indicating that they are participating in the reaction, but they're not actually one of the reactants or the products. So sometimes you'll see like heat listed here or an acid listed there. So platinum is the primary catalyst here. Again, the whole idea with hydrogenation is that this hydrogen is walking over that double bond and turning it into a single bond. So tomorrow we'll look at just a couple more of these reactions. We'll also talk a little bit about aromatics, and that'll close up for us fully chapter 11 here. And so last note I wanted to make is there's a reason this post lecture was set for Tuesday night. That was because I wasn't sure I was going to get finished today. I had a little bit of good judgment there, I guess. Nonetheless, tomorrow we'll finish it. We'll also begin to look at alcohols and ketones, which is the subject of chapter 12. And we'll just kind of take it piece by piece from there. See you tomorrow.